Okay, so let's continue working in Chapter 9. And last time, remember, we talked about hypothesis testing and confidence intervals for two sets of data at the same time. So you have X and you have Y, and you can form something like the sample mean, X bar, and sample mean, Y bar. And those are approximations for mu1 and mu2. And then, of course, when we take the difference of X bar and Y bar, we can study the sample statistics and get an idea for what's going on with the population difference, mu1 minus mu2. So today we're going to talk about the specific case where we have paired data. And by paired data, we're thinking that the sample sizes are the same. Remember last time we didn't allow the sample sizes to, in general, be the same. So now we can have m equal to n. And of course, there's a lot of ways where interesting problems arise where we actually just have m equal to n. It could be the case that the data is paired in some natural way, maybe a controlled experiment where we have two identical sample sizes. Remember, we looked at one of those examples last time where we did have a controlled experiment set up, but for different reasons, it might be the case that when we actually have the data, m is not equal to n. But of course, in general, we like the case where m does equal to n at the end and nothing unexpected arises when the data is collected. Alternatively, we might be studying two observations about the same n individuals, and in some way they can be paired afterwards. And toward the end of this section, we'll actually look at a neat example where we consider twins and looking at twin data where genetic factors are almost identical, but maybe one little change in their genetic variation or whatever the circumstances may be give us a great way to study the differences in the two samples. So let's just look at a motivating example first. Trace metals in drinking water affect the flavor, and unusually high concentrations can pose a health hazard. Considering zinc in the water in this example, they're going to take 6 river locations, and we're going to look at the zinc deposits both at the surface of the water and at the depth of the water. And when we do so, you get a little table of data. Okay, and notice here that there's 3 levels of data being reported. The first is the bottom. The second is the surface, and the third, it's not actually any new data, but we're reporting the differences. So if you just took the bottom and the surface quantities and took their difference, that's how we're forming this third row of the data. Okay. Now, we could ask questions about this once we have the data. Is there any significant difference between the surface zinc levels and the bottom zinc levels? And if there are, then maybe we can use that to say a little bit more about the way that the river is polluted, for instance. So let's look at the data, and since it's a short enough list, we can get away with something like a dot plot. We could have also done a comparative box plot, but in this case the dot plot does just fine. And what we're looking at is the bottom surface zinc levels are the top dots just above the line, and then right below the line, that's the corresponding surface measurements. Okay, nothing too much to say. There's quite a bit of variability, but as you can see, maybe you could say, for instance, that the X data seems to be shifted to the right a little bit of the Y data. That confirms our suspicions, or at least it begins to tell us at least that X might be greater than Y when we look at the average values. Now, what the top graph doesn't do, but this bottom graph does more effectively, is it pairs the data. So these numbers that we see that show up, it's the same dots, but these numbers tell us the locations at which the measurements were taken. So if you look, corresponding to 1 here, right, that's the first river location. The X and Y samples are pretty close, but then for 3 and 4 in particular, there's quite a bit of difference between the zinc measurements in those other locations. But overall, everything's fairly well paired. The one thing to notice, though, is that every single X location, it's bigger than its corresponding Y location. Okay, that wasn't as clear from these dots. It could have been the case that this X corresponded to this Y. We didn't see that. But as soon as we identified which pairing of the data made sense, you could see this trend immediately emerge. And by the way, if we go back to that last slide, let me do that really quickly. The reason that X is greater than Y for each location is because these differences are always positive. Okay? So this is the point. When we're looking at this example, the first thing we notice is that a natural way to study the data is to look at the differences themselves instead of looking at the data as two different sets. Okay, this is something that's unique to the case where m is equal to n. And so rather than studying x and y separately as we did last time, we're just going to study the differences. And now, instead of 2 samples of data, we really kind of only have 1 sample of data. We're going to gain some strength in terms of testing. We can go back to last chapter. We can go to chapter 8 and apply those methods to study hypotheses for the difference of the means now. One of the disadvantages that we'll see is that we lose independence for our data most of the time. So we won't necessarily assume that to be true. But here we have it. So these d's will be the new quantity that we study, and it's the pairwise difference of x and y data. Okay? So yes, again, we won't be able to assume independence. This is the consequence of that. Remember last time we talked about how the standard deviation, when we took v of x minus y, the variance was sigma 1 squared and sigma 2 squared. We sort of had this Pythagorean theorem looking expression for the standard deviation. We won't be able to use that here. Luckily though, we won't really need it. So we'll have to see what other methods are of interest when we have this paired data now. Okay, so let's begin by looking at our d sub i's now, the differences of pairwise data, x and y. And the average or expected value of these differences is mu1 minus mu2, which we could have also gleaned from just taking x bar minus y bar and talking about what we expect those to be on average. It's the same value. Okay, but now we're going to just study mu sub d as a single quantity, and it's the expected value of these differences d sub I. Okay. Now, we will not rely on the 2 sample t-test. We will rely instead on the 1 sample t-test to do hypothesis testing. Okay. The other thing we'll need to know, though, is sigma sub d. And remember that when we work with the standard deviations, when we had 2 samples as before in sections 9.1, 9.2, that sigma came from being able to assume independence. So this sigma d will be much harder to calculate in general. Luckily, we're using the t-test, and if you remember, we get those larger tails than we do for the z-test when we talk about the t-test. But the reason is that we're always using the sample standard deviation rather than the exact standard deviation. So in this case, it won't really hurt us so much, as we'll see. So let's think about a hypothesis test now. I'm thinking that for my paired data, the difference on average is delta naught. Okay, delta naught is my null value for that difference. And when I do that, I can form a t-statistic. Okay, we're going to just replace sigma with the sample standard deviation, wherever that may be. Divide by root n again. Okay, and when we subtract off delta naught and divide by s sub d, we have a standardized variable. And because it's s in the denominator, we might have a small sample size. We think of it as a t statistic rather than a z statistic. Okay? And if you remember from last section rather, the degrees of freedom was always much harder to calculate when we had 2 different sample sizes. Well, that goes away too. This is really very much like the 1 sample t-test, where the degrees of freedom is just determined by n minus 1 in this case. Okay? So let's think about the 3 different cases that we can have for alternative hypotheses, upper, lower, 2-sided tails. And when we look at everything, this slide, again, a lot of these slides are very similar. This one is basically right from looking at the t-test from chapter 8. If you were to go back and compare to that slide, very similar. These should be in terms of the t distribution. I think that's a small typo, so just be aware of that. But when we have a greater than, we're using the upper tail to compute the probability, and therefore the p-value is computed by taking the t.dist function, or if you were using Minitab, you would go to Calc, Probability Distributions, drop down to the t menu. Then you'll take 1 minus that value to get the p-value. For the left tail, it's simpler than that, and for the 2-sided tail, you have to split the difference. You have to double the quantity that you get from the t distribution directly. So let's look at an example where we actually compute a hypothesis test and test some concerns. So this is for staff workers, okay, who work in front of visual display units. All right, and basically what we're looking at here is the fact that a lot of people, when they work, they have a limited range of motion, And we're hoping that by varying the work conditions that their range of motion will increase and therefore the overall health of workers will increase. So the way this experiment was set up, we're going to look at the data. They look at the arm elevation, and if it's more or below 30 degrees, okay, then the worker is sort of inactive, and we want to try to get their arms moving around a little bit more. So 30 degrees will be the cutoff, and now we're going to look at the proportion of time that workers had their arms raised to a certain degree angle. Before and after work conditions were varied. They had an 18-month window in between. Okay, and so this is a very nice natural pairing of data, right? In fact, in this case, there's no real danger of suddenly losing one value in X for the sample and not Y, right? Because if we have one person's before, we're certainly going to have their after measurements. Okay, so these are proportions. They're thinking of them in terms of percentages of the time during the day that the workers are being measured, where they had their arms raised to a certain elevation. And if we look at the differences, that's what we're going to focus on when we do our hypothesis test. Just gleaning right now quickly, we see a lot more positive values than negative values. Okay, and if you look at what that means in terms of the data, it means that the workers had their arms lower a higher proportion of the time before. So we're already getting a pretty good idea just from the data that these workers are probably more active after the work environment was changed accordingly. So let's see if we can use the data to determine whether this is statistically significant. Okay? Now, when we have a small sample size like this, it's very important to make sure that we go and check that everything is normally distributed. So, let's see. What I'd like to do is let's back out, and I've already copied and pasted the differences into a Minitab file. So let's go ahead and first of all get some basic statistics, and I don't know, let me do a graphical summary. That tends to give us a lot of nice information. So here's my differences for this example, and we can use a 95% confidence interval. That'll just give us some extra information at the bottom of the slide, or the bottom of the screen rather. Okay, what I'm really looking for right away is in this top corner, the normality test. We have a nice high p-value. Okay, and again, if you want to think about this, you could, in loose language, say that the p-value is the percentage of which our hypothesis is likely to be true. Right? With a low p-value, we tend to reject the null hypothesis. This hypothesis is whether or not this data looks like it's normally distributed. You can see this quite nicely visually, right? Because the bell curve that's fitted over the data seems to match pretty nicely. It's kind of over and under the bars. That's good. So this has definitely told us that we can assume that this data is normally distributed. Additionally, we have the sample statistics. We'll make use of those. Okay. If we're computing things by hand, we need those. But what I'm going to do next is let's look at a t-test in Minitab. And again, since we have really just one set of data that represents both x and y, we can use one sample t-test. Whoops, I clicked on two. We can go to a one sample t-test. There we are, one sample t. Okay, and again, navigating the menu, we have column data, so when it prompts me, I can put that in. Oh, hypothesis test. Let me just make sure that we're testing what the slides are testing. I think we're going to go for 0. Yes, we're going to go for 0, okay. I think that the difference is 0. Let's prove otherwise with the hypothesis test. This all looks fine. Okay, and I click the button. They give us the t statistic. That would match up nicely if we were calculating everything by hand from the data. And we get the p-value. Again, this p-value is very small. And so, do we reject or not reject the null hypothesis? Right? We reject the null hypothesis, at least if the significance level is anything reasonable. Right? Normally we only go as low as 1% significance. The p-value is less than 1%, it's a 0.5%. So, again, we conclude that modifying the work environment had a significant effect, because the null hypothesis said otherwise, said there was no effect, but we rejected that because the p-value was low. Okay, so that's summarized in the slides, the little test we just performed. And now that we've talked about a hypothesis test, we could also look at confidence intervals for paired data. And this is actually, again, much nicer than what we saw in sections 9.1 and 2, where we would have had x bar minus y bar instead of this little d bar. T is the same. SD, remember this would have been this complicated expression where we had the square root of S1 squared, S2 squared, and of course nu, that complicated formula for the degrees of freedom, well, that's just n minus 1 now. So this is a much nicer test to run. We really do prefer paired data whenever possible. It simplifies matters quite a bit. Okay, so this is our general form for the confidence interval. Really nothing new here, nothing to point out or add other than the fact that paired data simplified a two-sample test. Yes, if n is greater than 40, then we can safely replace the t calculation with a z calculation, because then we're relying on the normal distribution. So let's look at an example where we construct a confidence interval. This one's for medical records. And what they're testing in this case, if you read the example, is that doctors are still getting used to what's happening in the medical profession, where we're switching from printed out medical records and images of tests that were performed over to digital. So right around when this was really transitioning in the early 2000s, they ran a small sample size to just see how effective it would be to completely switch over to everything. So they were testing whether or not this was going to be viable at the time. Of course it is, and as we live in this world now where everything is becoming digitized, tests like this were important to conclude we were moving in the right direction. But let's take a look at it. So 13 computer proficient professionals were asked to retrieve medical images of some sort. They had two ways that they were doing so. One was from slides that we're actually thumbing through and physically removing the medical tests. Maybe they were x-ray slides or something like that. The other alternative was just go through a computer database with a web front end. So these are the times it took to retrieve each medical image, and I'm guessing this is in hours. No, probably in seconds. But as you can see, a clear trend emerges right away. The differences are all positive, and in this case, in that context, it tells us that, of course, it's taking them longer to retrieve the slides than it is the digital files. So the real question here isn't so much whether or not the difference is on average 0, but rather, well, what is the difference, and how confident am I that this difference is correct? All right. If I average these numbers, we get a point estimate. Let's build an interval that gives us some degree of certainty around that. I won't go through the same test that we just did in Minitab this time, but the same idea applies. We always have to test for normality with small sample sizes. We only have 13 in this case. The p-value is 0.31, so that looks fine. So we can reasonably assume that the t-test applies to this data. Okay, so with a 95% confidence, the interval, by the way, comes from the graphical summary. We could go back and compute this by hand and double check it, but at this point we've done a lot of examples where we've used the by hand calculation. So this is rather nice. Everything that we need is here. The confidence interval is right here. The sample mean, the point estimate, is the center, of course, and the distance here is determined by two things. One is the significance, the confidence level, 95%, and the other one is the sample size, right? So in order to reduce the width of that confidence interval, we would have to increase the sample size. But we can definitely say that, let's see, between 13 and 28 seconds are saved on average by retrieving the medical images from a digital database rather than slides. So again, that was a nice example of how the digital age improved medical practice. As I said earlier, we're going to do a neat example. We're just going to look at this. It's sort of fun. When you actually have the slides in front of you, please take a look at the links. They're also fun to look at. But there's actually a place called Twinsburg, Ohio, and it's really neat. They have a parade every August, I think it is. And here's just one picture from the website. If you click on the link, you can find more. The particular photographer is Charles Robinson, so felt obligated to include his website in particular. But it's kind of a neat gathering. Since my niece and nephew are twins, I might take them there someday, in fact. But let's take a look at some interesting things that statistical investigators might be interested in. Okay, so for instance, at this very festival, scientists go every year and they sort of poke and prod and bother these twins to do studies of certain kinds. If we think about it in terms of genetics, twins are, odd mutation aside, they share 100% of their genes, so they're basically clones. But the odd mutations, well, if you think about the frame of what we're studying right now, those differences are exactly what we would love to isolate, and maybe they can tell us something. There's many examples where this sort of study has been conducted. And let's see what's on here. I forget just offhand. Yes, genes and experience. Yeah, so flavors, for instance, even before birth, people are exposed to flavors such as chocolate, garlic, etc. Okay, and though it's not clear whether such prenatal exposure shaped taste perception, there is evidence that it shapes preference for foods encountered in life. So maybe this is a good place to test. Well, how do the way I taste food differ? Maybe if one twin has a different set of tastes than another, then that's environmental rather than genetic. So these are neat things to do. There's other ones, and let's see what else is worth mentioning here. I think I'll just let you read this, but yes, talking about different tastes. Yes, and leading into the example we're going to look at, another fairly well-studied concern is that of just in general mental wellness and mental health. It turns out that a lot of mental disorders are environmental rather than genetic, and there's often the case, as we'll see with schizophrenia, that one twin will develop the disease or condition and the other twin will not. So we have a nice natural pairing of data where we can study things. In particular with schizophrenia, there is the temporal lobe, and inside of the temporal lobe is the hippocampus, which is what controls our memories. And schizophrenia, it's well documented, has an effect on the hippocampal anatomy, the way that our memories are processed. The overall structure of the hippocampus is affected by schizophrenia. So what we're going to look at next is twin data where one of the twins has schizophrenia, the other one does not, and we're just going to study the volume of the hippocampus in each twin. So the unaffected twins, this is the volume for their hippocampus in the brain, and the affected twins is the bottom one. And as you can see, there's quite a bit of a difference, in fact. Right? Most of these differences are positive. We have one negative. Some of them are very close to zero, but there may be something significant here. So let's find out. Okay. All the differences are positive. That's not true. That's demonstrably not true. I have to check into that comment, but that's fine. But let's test if there is a significant difference statistically. So we could do a t-test for this. And yes, this is not actually done in the slides, but you could feel free to just drop these differences into a spreadsheet, and we'd find a p-value of 0.003, okay, which means that we reject the null hypothesis that the difference is statistically zero, and there is some statistical significance to these differences. They're bigger than zero in general. So this gives us reason to believe that, yes, in fact, schizophrenia does affect the hippocampus. This more or less is a study to confirm that fact, because here you have twins. They're identical in almost every way, shape, and form, but their hippocampus have a statistically different size. So schizophrenia is can be identified as the causative factor in this case. Okay, so let's take a short break, and then we'll talk about section 9.4.